Hello and welcome to Empowered Learning. This video will be about using indefinite and definite integrals in solving differential equations. To be more specific, what we're going to do is do a deeper dive into what we call directly integrable equations. Those are the first order, and we're going to study solving directly integrable equations by using both indefinite integrals as well as definite integrals. And we're also going to see how do we deal with solving directly integrable equations that are defined as a piecewise function. And so there are going to be some other things that we're going to mix in here as well, as far as some well-known functions that we use, especially those that are piecewise or those that may not have elementary antiderivatives. And of course, when we get to those points in our discussion, you'll see where they fit in. But the main thing that we want to concentrate on now is just making sure that we know that whenever we're dealing with directly integrable equations, that we can also solve those types of equations, especially whenever we have initial conditions by both using indefinite integrals and definite integrals. So if you're wondering, well, what does it look like to solve a directly integrable equation using indefinite integrals? If you go back and you watch my video on differential equation basics, you'll see that I've actually went in and defined what a directly integrable type of, well, not defined, but I've show you what a directly integrable type of equation is there. And all the problems that I did in that video where we had to take antiderivatives, I was using the indefinite integral process. So we're just going to reiterate that here, and then we're going to show how we can actually solve initial value problems by using definite integrals to be able to make everything compact. All right, so first thing we want to talk about is what is a directly integrable first order ordinary differential equation. So in essence, it is just a first order ODE, and it's considered to be directly integrable if and only if, that's what the IFF here stands for, if and only if the ODE can be rewritten in this form. And so basically what this means is that we take the first derivative of the function with respect to x is able to be written as just a function of x, or in general, just a function in one single independent variable, okay? Now, if we're dealing with, let's say, a third order, fifth order, ninth order differential equation that is of the directly integrable form, then of course, whatever that is, it still has to be equal to a function of just one single variable, okay? And so please note that when we say it has to be a function of one variable, again, we do not mean, let's say if we had a situation where we had dy over dx, and let's say this was f of y, this would not constitute as a directly integrable type of equation, okay? And so we're assuming here that y is a function of x. So whenever we say it is a function of a single variable, whatever this variable is, it has to be the independent variable that is referring to the derivative in which is being taken with respect to, okay? So we want to make sure that we know that difference here, okay? All right, so knowing that an ODE or PDE is directly integrable means that you can use indefinite or definite integration techniques from calculus to find solutions to these equations. And to be specific here, you would want to use the definite integration type situation whenever you have an initial value problem. And let's just say that you're going to come to an output in doing that work to where you're going to be asked to integrate something that doesn't necessarily work very easy. And what I mean by that is something like, let's say if you were asked to integrate something like this, okay? Well, we know that e raised to the x squared does not have an elementary antiderivative, okay, meaning that we can't express it in terms of the functions that we're used to seeing. We would actually have to rewrite this in terms of a power series or a Taylor series, and then do the antiderivative by taking the polynomial approximation for that. And so we don't want to go through all of that. And so and that's part of the reason why we're going to introduce some special functions that tend to pop up in a lot of applications that we use differential equations for. And so in those instances, that's where we really want to use this definite, the definite integrals. And so when we get to that point, I will let you know. So as an example here, we're going to go through this example to where we're going to look at all of these first order differential equations, and we're going to see if they are directly integrable or not. If they are, we'll explain why. If they aren't, we will explain why. So let's look at A. So we see that the first derivative of y with respect to x is written as -4. Let me get my pen straight here. As -4 plus tangent of x. And so notice that this can be considered just a function of x here. So since it's considered just a function of x, I can say that yes, that is directly integrable. Okay. Now for B, I would have to say that it is not directly integrable, because do you see how our independent variable here, well, it's really not an independent variable. It's the same as our function here. So we don't have an x here. So because of that, this is not a function of x, or a function of the variable that we're taking the derivative with respect to. So this will not be directly integrable. Okay. Now, in this case, to be able to get this third equation in the form, we would have to divide both sides by y. And if we did that, we'll have dy over dx is equal to 3 divided by x times y. And this is a function of both x and y. So, of course, that's not just a function of x. So that means that will not be directly integrable. For our fourth equation, we could divide both sides by x here. And if we did that, of course, this would reduce to 1 over here. And this could be considered just a function of x. And so because of that, this would be a directly integrable type of equation. For E, we see that we have a second order differential equation. But notice that this will not be able to be written as d squared y over dx squared equals to some function of just x. Okay, so notice that that won't be able to happen here. If we were to try to rewrite this, and I'll just kind of write over what we have here, this would be equal. Let's try this again. This would be equal. This would be a -3. This would be a -8y. And so now notice that this would be a function of x, a function of y, and a function of the first derivative of y. And of course, that's not the same as a function of x. So that's why that particular equation would not be considered to be directly integrable. All right, so for this last one, same kind of thing. We could rewrite this, and let's say if I just rewrite this as y double prime, this is y prime, then what I would end up with is y double prime is equal to -3x y prime, all that divided by x squared. And of course, this would be a function of x, y, and y prime, which is not a function of x. So we would not consider that to be directly integrable. All right, so now that we are familiar with what a directly integrable equation is versus one that is not directly integrable, we're going to continue our discussion about using these types of equations by solving these types of equations by using either indefinite integrals or definite integrals. Now, as I mentioned before, If you've taken first year calculus and you first learned about antiderivatives, or you watched the video that I had on differential equation basics, then you're familiar with what it looks like whenever we are solving directly integrable type of equations using indefinite integrals. Okay. In short, as I said before, we want or you can use indefinite integrals to solve directly integrable initial value type problems, as long as in the process you're able to pretty much work out what the antiderivative of whatever it is that you come up with in the process of solving that differential equation. If you end up in an instance to where you know that you're going to run into some kind of brick wall where you're like, yeah, that's going to take a lot to try to actually figure out what the actual antiderivative of that is, and or if you have a situation where you know that you're not going to be able to find the antiderivative of it, of some expression in your work, but it is a special type of function that has been identified as one that's been worked on and that's popular, then you want to use definite integrals in that case. Okay. And so all that I mentioned here on the second page is that if we have initial conditions, and of course, if we have an nth order differential equation, we're going to have n initial conditions, starting with the original function all the way to the n minus 1th derivative. That could be possible. Notice that there are times if you use indefinite integrals that you may forget to write the arbitrary constant, or let's say you may rename the arbitrary constant C, and then you use C again and you forget which C is what. In those instances, if you know you have those issues, that would be another situation where you would probably want to defer to using definite integrals to solve initial value problems. And so that's pretty much all this paragraph here says. Now, if we're going to solve directly integrable equations by using definite integrals, then I want to kind of go through the short derivation process to show you why and how we're able to do that. And this is mainly so that you know whenever you're faced with a situation like that in a problem, you know how to set it up properly so that everything flows smoothly. Okay, so we'll just read here. So let y of x be a general solution to an ordinary differential equation. And of course, we know that this is going to be directly integrable by definition. Okay, so if we know that dy over dx is equal to y prime of x, meaning that whatever this function is, we know it's just a derivative of what it is that we're looking for, then we could rewrite this function this way. Okay. Now, essentially, all you're really doing here, and I know depending upon if you're taking a differential equations course or not, some people are very particular about this, but essentially all you're really doing here is multiplying dx to both sides. Now, in all actuality, that's really not what you're doing. And I'm only saying that because dy over dx, it can be translated as y prime of x. So this really isn't something that you can break up. But when you start to do a deep dive into what the actual definition of dy over dx is, you find that, yeah, you actually could break it up depending upon how you interpret it. Okay. Now, the reason why we're able to take this particular equation here and rewrite it into the form that I have underlined here, even if we are taking the fact that we shouldn't break up the dy over dx into account here. And let me get my pen working again. The reason why we're able to do that is because what you're seeing here is actually the definition of what we call a differential. Okay. And in first year calculus, we use this expression to sort of estimate what the change in y values would be from one x value to another. if we know explicitly what the derivative of a function is, and this dx here, which is theoretically, this is the smallest change in x values that is allowed if we allow this to be a delta x, where let's say delta x may be like 0.1 or 0.5 or something like that. Okay, so we use this particular formula here to be able to basically estimate change in y values. And another thing that we use it for is to sort of rate or measure the sensitivity of our particular function y with respect to changes in x. Okay, so for that reason, we're able to take this particular equation and rewrite it this way. Now, of course, the simple informal way of doing it, again, is just to say, hey, let's multiply dx on both sides and everything will be all right. And for most of what you do, if you're taking a differential equations course, or if you're having to work in differential equations, that is fine. Okay. So from here, of course, we would want to integrate both sides. Okay. And of course, if I do this, then I'm doing an indefinite integral because I don't have limits of integration on my integration sign here. And we know by definition that if I take the antiderivative of the derivative of a function, it's just going to be the original function plus that constant. Okay. Now, we know this, but what if we wanted to actually put some limits of integration on this? Okay. How would we be able to deal with that and sort of wrap it up to make it be nice and concise if we were doing an initial value problem? Okay. Well, the suggestion that we have here is let's kind of look at this problem again, but we're going to let x equal some other dummy variable s. And s, we're going to allow that to be the variable of integration, just like x was here. And the only reason why we're changing this is to make x and s look different, even though they're going to act the same way. The other thing that we want to do here is we want to allow the upper and lower limits of integration to be a and x respectively. Okay, where a is going to be a constant value, x is going to be the same x that is here. Okay. Now, if we did that, then of course our dy over dx, or the derivative of y with respect to x, would look like this. And everywhere where I have x, I can replace it with s. And of course, that's what you have here. And then of course, from all the stuff I said earlier about, we know from this equation here, we can rewrite this in its differential form. We can have this. Okay. So now the idea here is, what if we wanted to not solve for y, but solve for y with some initial conditions? And so if we did that, according to what was suggested above, we would want to do something like this and see what the outcome would be. Okay. Now, if we did that, then of course we end up with this situation here. And just as I have described earlier, if I take the antiderivative of the derivative of a function, I'm just going to get the original function back. And from first year calculus, we're going to use the net change theorem to be able to evaluate the antiderivative at the upper limit minus the lower limit. Okay, and so that's exactly what we've done here. We know that since a is a constant, then y of a should be some particular number. So we're just going to call that c. Okay, so we see here that the definite integral of 1 dy going from a to x is going to be y of x minus y of a, or c. Okay, and again, c is just some arbitrary constant. So by us knowing specifically what this is, and in initial value problems, you'll be given that information, we could substitute that value directly into our equation here. Okay, and so in doing that, what we end up with is saying that y of x can be defined as the definite integral of the derivative of y of x, where the integral goes from a to x plus whatever this constant value is here. Now, the reason why we're able to do that, let's take a step back here for a second. The reason why we're able to do that is because remember that all of this is equal to that. And of course, what this is here is the same thing that is. Okay. So essentially what we are saying here is that what we have here can be put in place of what you see there. Okay. And so when we put this yx minus c in place of that, what you end up having here is, and I'll just write it out here. So you're going to have y minus, I'll just say c, is equal to all of this business here. Okay. And remember that x and s are actually the same exact thing. So I could take these s's out and replace them with x's because they are essentially the same. And so if I added c to both sides here, then you'll see that what I have is just y of x, and then I have definite integral of the derivative of y with respect to x from a to x plus c. And that's exactly what we have here, where the y of a is equal to c. Now, why are we going through all of this? Okay. Again, this is a nice compact way for us to express what y of x is in terms of the definite integral of its derivative plus some constant. If we're doing an initial value problem, we will know what this constant is. And then on top of that, this becomes real useful whenever we're dealing with some function here, to where if we try to take the antiderivative of it, it would be very hard to do. Wouldn't be impossible, but it would be a situation where we would probably have to use, let's say, Taylor or Maclaurin series or some binomial series to be able to rewrite it and get a polynomial approximation for it. And we just really don't want to go through all of that. Other times, you'll have situations where you'll have special functions, and of course we're about to see those in just a second. We'll have special functions that we know, hey, we don't necessarily need to take the antiderivative of it. We kind of know what it is, what it's going to be, and we have either tables or graphs to help us out with that, and it's advantageous for us to leave it in that form. So that would be situations where we would want to do this in, okay? And so that's essentially the points that I'm making down here. Either we want to make sure that, again, if we use definite integrals, we don't have a situation where we're confusing what we've named our arbitrary constants if we have multiple of them. And we have a situation here where, again, the functions that we're dealing with are kind of hard to deal with, or they're specially defined functions to where we really don't want to go through the pain of trying to take the antiderivative of it because they're defined in terms of integrals. All right, so special functions to know. So the functions I'm going to introduce here are some that they tend to find themselves popping up a lot in a lot of applications. My background as an engineer, I see these types of functions a lot of times in signal processing or heat and diffusion equation type applications. But again, just want to introduce you to the functions. So this first one here is called the error function, also known as the Gauss error function. Notice that the function is defined in terms of a definite integral. And so again, if we have a situation where we're working to solve a differential equation and we know that one of our terms is going to look something like this, instead of us actually trying to figure out what is going to be the exact area under the curve of that particular function. We're just going to leave it in that form and call it the error function, and we're going to refer to either tables or graphs to be able to figure out what that result would be. Okay. Another function that tends to pop its head up a lot in applications would be the sine integral function. And so another way to define the sine integral function, it is the definite integral of what we call a sinc function, which is just sine of, I'll say x divided by that same variable x. Okay. The sinc function, I have personally named it what I call the drum whack function. And I call it that because of how it looks and what it simulates. And so this particular function, I'll draw a quick sketch of it right quick. It kind of looks something like this. And the whole idea is that if you have a sound, and I'm going to make a sound here with my pen. So if I do like this, we notice that we heard the sound for a split moment, and then that sound went away. And so that's essentially what the sinc function is trying to communicate to us. Now, of course, if we're doing the definite integral of this from 0 to x, then what we're really trying to do is find the area under the curve of this function from 0 up until, some value x that we define. Okay. And so again, to deal with this, we could try to take the antiderivative, but again, it's going to be a little difficult to do. Not impossible, just difficult. And since we already know kind of how this function acts, we have graphs or tables that will help us be able to figure out this particular answer here. So it's just more advantageous for us to just refer to it as psi of x, okay? Or si of x, right? All right, so now that we are familiar with those two functions here, let's look at an example of how we can actually use these techniques of using definite integrals to solve directly integrable equations and these special functions to be able to have nice compact answers for your differential equation. So we want to find the solution to this initial value problem where here's our first order differential equation and here's our initial condition. So basically when x is 0, y is 0. So the first thing that we notice here is that we could rewrite our first order differential equation in this form, which means by definition, it is directly integrable since sine of x squared divided by x is indeed a function of just x, which is the same variable that we're taking the derivative with respect to for y. The issue here is that although it's directly integrable, it is not that easy to take the antiderivative of sine of x squared over x. Okay. At first glance at it, what we would probably think to do is to say, all right, well, I want to use substitution rule. Okay. So you basically think of, all right, I want to take antiderivative like this. And I know that if I have this and I have dx on this side, make that go away, then I'm going to do substitution rule. And you'll let u equal to x squared, which means that du is equal to 2x dx. And so that would mean that essentially you would have this situation here. Well, if you did that, then of course you have something to replace this with, but you don't have anything in terms of u to replace 1 over x dx with, okay? So that in lies the problem that we have, okay? And so if we were to, rearrange this to try to solve for 1 over x dx, it would be kind of hard to do because, of course, this x is in the denominator, so there's no way I'm going to get x in the denominator on the same side as dx being in the numerator, okay? So that sort of crushes that idea. However, we could use the fact that, hey, I know that if I could have sine of x squared divided by x squared, somehow that might work. And so here I could multiply this by 1, but make 1 look like x squared over x squared. And then from there, of course, switch the places of these two expressions here to where now this looks more like a sinc function in terms of x squared. And of course, x squared divided by x is just x, okay? And so now we have this extra x that's here, which is kind of what we saw up here that we needed, okay? So in this form, if I wanted to do, let's say, u substitution, I would have sine of u over u. And then, of course, this x part here, and we're assuming that we'll have a dx here, the x dx, if we got rid of that, that would just be 1/2 du is equal to x times dx. So we're saying all of that to say here, let me get my eraser working here. So I want to erase this part. So we're saying all that to say that this x times dx here would just be the same as 1/2 du, and everything would work beautifully at that point, okay? Now, that's going to be our basic approach, but instead of us just having the indefinite integrals here, in this case, since we know that in trying to take the antiderivative of this part is going to be an issue, we're going to use definite integrals. And what we're hoping here is that we're going to have some resemblance of this type function that pops up in our process of solving this differential equation. All right, so how do we do that? So what we decide to do is same thing that we said we were going to do here, but we're going to integrate, but do it with definite integrals where our lower limit is 0, upper limit is x. And again, we're doing that because if we go back to this page here, whenever we were deriving this process, these were the two things that were suggested for us to do to kind of, make this more streamlined. All right, so now if we actually integrate both sides and do the definite integrals from 0 to x, then of course this is what we have. We know here we're going to let s equal x squared. I know earlier I did everything in terms of u, but that was only because we're used to seeing u substitution in terms of u. But we can also do it in terms of any variable. So we're going to say let s be the substitution variable that we have. So that means that ds is going to be 2x times dx, which means that 1/2 ds is equal to x times dx, okay? So we have a way of replacing this with just 1/2 ds. And of course, this will be s, that will be s there. And so, of course, we'll figure out what the limits of integration here will be in just a second. So, of course, if we stick in 0 into here, that's going to give us 0. And if we, of course, if we stick an x in the air, it's just going to be x squared. Okay, so x squared is just going to be s. So what we could do here is just replace this with just s. And so now we see that our definite integral written in this form could also be written in this form, which could also be written in this form. Okay. Now, the important thing to look at here is that this particular integral here is the same exact thing that the sine integral function is, but it's defined in terms of s instead of x. Okay. And to be specific here, we know that if we had this situation, we could let s equal x. So if we let that be x, let that be x, let that be x. And again, we say that because we said it in the beginning that we was going to allow that to happen. So if that's the case, then what you actually see going on here is that we could take this particular function here and rewrite it in this way, okay? And so again, I'm just putting the x's here to let you know that this variable, and that variable all have to be the same. Okay. Now, the actual answer to this question, because in this case we said that x was actually going to be x squared, is we know that all of this is just going to be sine integral of whatever variable this is, which in this case is s. But back here we know that s is going to be equal to x squared. And again, we said that because that was the thing that we wanted to substitute s in for. Okay. So again, I know this may be a little confusing because I know I said here that x is equal to s here, but it's actually equal to s squared. But my point here is that we see here that the x squared is acting as the s. So whatever was on the inside here in the beginning, that's the thing that we're saying, all right, that's going to be the inside independent variable. And the point that I was getting at, and I'll skip back to where we were before, kind of make my point, is that when we were initially doing this, we said that s was equal to x here. Now, again, what I was trying to communicate is that for this particular function, when we do it, we're saying whatever the inside variable is, we're just going to replace that. Okay. And so if I look at, let me pause for a second here. All right. So here, if we're back here at the sine integral function, in this situation where everything just looks the way that it is, x is equal to s in this case. Okay. Now, if we said here that s was equal to x squared, meaning that we had a x squared here and an x squared there, then that means that this would have to be x squared as well. And this s here is technically, x squared as well. Okay. So whatever the inside variable is, that's why I'm saying that's what the inside substitution is going to be, and everything's going to be based off that. So in this instance, here we see that this and this look different, even though it is the same. In the problem that we were doing, notice that what we have instead is this situation. We have this, where x squared and s here are the same. Okay. So again, my whole point of sort of bringing this up here is if we just simply look at this, s is equal to x squared, and x squared is what the inside function is for our problem that we're working on. So we can use those things interchangeably to make everything look nice. So in this particular situation here, we know that integral from 0 to s of sine of s over s ds can just be written as 1/2 of sine integral of s. And of course, s is just x squared. And we know that that's a nice compact way of expressing our answer. Okay. All right, so the next thing that we're going to do is look at how to solve directly integral equations where the equation is going to be, let's say, dy over dx equals to some piecewise function. Okay. So when solving directly integrable ODEs, or any type of ODE for that matter, using piecewise functions, we need to remember that when performing the integration, we need to do the following. So here are some suggestions I'm giving before we start to do examples. 1, we need to integrate each piece of the piecewise function, making sure that each piece that we integrate is a function that is continuous over a closed interval. Okay. And so the reason I'm suggesting this is because in order for you to integrate a function, period, you have to have a continuous function over a closed interval to be able to do normal integration. Okay. Number 2, if the piecewise function has true discontinuities in it, the solution will not be valid at those discontinuities. Okay. So let's say for our piecewise function, we have a hole where we have a break in the two functions, or in between two functions. Of course, when the piecewise function switches off from looking like one function to another, or if we have a vertical asymptote, or if there's like a gap or anything like that, of course, the piecewise function, it translates to the solution not being valid at those places because the derivative would not exist in those places. Okay. Number 3, at the places of possible non-continuity, and I say possible because we could have some situations where the functions kind of trade off each other. And let's say you'll have a situation like this. And of course, we know where I'm drawing this point here, that may consider to be a corner. And we know that the derivative of a function is not defined at a corner, but it still is continuous. Okay. So what we would have to do in those instances is to take the antiderivative of this piece, take the antiderivative of that piece, and then make sure that the limit of both the left and right functions here are going toward the same y value. Okay. And so that would keep the solution to be continuous over the entire interval of x values that we're considering as well. All right, and so for number 3 here, investigating 3 will ensure that we have arbitrary constants for each piece of our piecewise function. And so you'll see when we go through this first example how that ends up turning about. All right, so before we actually get into some of these examples here, let's talk about some of the other special functions that we need to know of. One is a step function, or is also called a Heaviside function. You can kind of see here where x is equal to 0 until we get to values of x greater than 0, and then it steps up to 1 unit and then just stays there. So that would be what a step function is. And of course, this is what is defined in terms of a piecewise function. Your ramp function is just as it sounds. Okay, so we're going to be y equals to 0 until x is equal to 0, and then from x equals to 0 on up, it ramps up, and it's essentially the function y is equal to x. So here, piecewise, y is going to be 0 until it is equal to 0 or higher, and then it just looks like y equals x. So it ramps up with a slope of 1. If I had, let's say, 2 times ramp of x, then of course this would be looking like the function 2x here. So I would have, say, 1, 2, and 3, 6, if it was like that then. Okay. All right, your stair function. Your stair function is actually a variation of a theme on what we know as the integer function. Okay. And you may have seen the integer function defined this way. Probably not doing a very good job of drawing that, but that is another way that the integer function is defined. I think it's also defined this way. But basically what it is it is a rule to have you always round down to the closest integer. Okay. So for instance, if I had integer of 2.9, the answer to that would be 2, because if I always round down to the closest integer, rounding down to the closest integer for 2.9 would round down to 2. Whereas if I said integer of negative 2.9, then that would round down to negative 3. Okay. So in essence, what the integer function looks like, it kind of looks like a stair step. Okay. Looks a lot like what you see here. You just got a whole lot of. Okay. So it's like your step function, but you just continue on building steps on top of steps on top of steps. And so specifically for the basic stair function is just the integer function. And of course it has a vertical shift of 1 unit. Okay. And so, and that's because your basic integer function, so in between 0 and 1, your function looks like this. and then at 1 looks like this, and then at 2 it looks like this, so on and so forth. So you can see, to be able to get this part here from being down at y equals 0 to y equals 1, I would have to vertically shift that up 1 unit, and hence why it's here, and why I'm saying the stair function is really just the integer function plus 1. Okay. And again, here, piecewise, we see that as long as x is less than 0, y is 0. When x is in between 0 and 1, including 0, of course, y value is 1. In between 1 and 2, oh, sorry, what, let me make, yeah, this should be in between, yep, 1 and 2, not 2 and 3, okay? So in between 1 and 2, this should be 2, and then of course for 3, this would be if this is in between 2 and 3 here, and that this part here would just be less than, okay? All right, so that's how that works. And so we'll be using these types of functions in our process of trying to solve directly integrable type of ODEs where they're defined as piecewise functions. All right, so now what we're going to do is a host of examples to where we're going to solve these initial value problems, either using indefinite integrals or definite integrals. Again, we're going to start off doing indefinite ones, so it's going to be kind of similar to what you've seen in the previous differential equation basics video, or in your first year calculus course where you initially learn how to do antiderivatives. Going to see those kind of situations. Once we get a little deeper, I'm going to identify situations where we could possibly use definite integrals to be able to figure out the solutions to these initial value problems, and we'll utilize that particular technique when necessary. All right, so for this example, the first thing that we want to do is try to get this into a form that makes it easy for us to solve it. And so since we see that we have two terms on the left side, and one of those terms just has dy over dx, we could rewrite this as a directly integrable type of equation here. So if we were to add sine x to both sides, we would have this. And then, of course, if we divided both sides by cosine, then what we would have is dy over dx is equal to tangent x, okay? And so, of course, from here, we could say that this means that dy is equal to tan of x dx. And so from this point, we could figure out what the antiderivative of tangent is without not too much difficulty. You could either look at an integral table or just memorize what it is, or you could use a substitution rule to be able to figure it out, okay? So I'm going to assume that you don't know what it is, and I'm going to use the substitution rule to figure it out. So I'm just going to say integral of dy is equal to integral of sine x over cosine x dx. Okay, and so here we'll let u equal cosine of x, and that's going to imply that du is going to be negative sine x dx, which means that minus du would be equal to plus sine x dx. So for here, on the left side, we know that the antiderivative of 1 dy would just be y, or y of x plus some constant, okay? Over here, and I'll just call this C1 for now. Over here, I know that cosine is going to be u. sine of x dx can be replaced by minus du, okay? And of course, whenever I finish integrating this, I know that this is also going to give me another constant as well. So since I know that, I'm going to have a constant on both sides. I could just make my life easy and just allow that to be just one constant all on the right side, okay? So we have this situation here. This basically ends up being negative 1 over u du, which we know this is minus natural log of absolute value of u plus, let's say, that constant c. And from here, we know that u was cosine. So we could either say this is negative natural log of absolute value of cosine x plus c, or we could use our logarithm properties, take this understood negative 1, put it in the exponent here, and have cosine of x raised to the negative 1 is the same as secant. And we can say natural log of absolute value of secant of x is plus c. So that would be our most general solution to this. Now, since we were able to take the antiderivative with relative ease, then here we'll just use these initial conditions. So we know that y of 0 is equal to 3, which means, and I'll use this form of it, that negative natural log of cosine of 0 plus c is equal to 3. We know cosine of 0 is 1, and natural log of 1 is 0. And so that essentially just ends up being c is equal to 3. So then our final answer just ends up being y of x is equal to negative natural log of cosine of x plus 3, or natural log of secant of x plus 3, where of course we have the absolute values. This would be your answer to this particular ODE. All right, so for this next example, we see that we have x times the second derivative of y plus 2 is equal to square root of x, and we have two initial conditions. Of course, for this one, we'll take the same approach. We'll rewrite it, and we'll essentially end up having, and we'll have the second derivative of y, x squared is going to be equal to some function of x. Going to probably have to take the antiderivative twice, figure out what it is, and then after that, apply these initial conditions. Since this one is a little long, I'm going to go ahead and just go over what I've already written out, and so that we can just kind of see the process for how this flows, and then we'll just move on to the next example. So we see with this being written out here, we're going to let our second derivative here be replaced with y double prime, and let square root of x be x raised to the 1/2 to make life easy for us. We also see that in thinking about this, that for square root of x, x could be greater than or equal to 0. But notice here, I would not be able to divide by x unless I knew that x could not be equal to 0. So for that reason, we know that for whatever solution that we get, we're not going to be able to have x be equal to 0. And of course, it's not going to be able to be negative. So that result basically says that whatever x is going to have to be positive, okay? And so we keep that in mind as we go through this problem. So this is our differential equation rewritten in y in prime notation. And so now all I'm doing is just basically solving for y double prime. So this step here, I subtracted both sides by 2. This step, divided both sides by x. And here, when I simplify, I get y double prime is equal to x raised to the negative 1/2 minus 2 divided by x. And again, we could see right here that x would not be allowed to be 0 in any one of these situations. Of course, x can't be negative because of the square root part up here, so that's why x would have to be greater than 0. So we have y double prime times dx is equal to x raised to negative 1/2 minus 2 divided by x, all that times dx. And so we just need to take the antiderivative of both of these terms twice. Okay, so we take the most general antiderivative of y double prime to get y prime, and we see just using basic antiderivative rules that we end up getting 2 times x raised to 1/2 minus 2 times natural log of x plus c. And notice here that in this step, I have absolute value signs here, but in this step, I don't. And that's because I recognize here that x has to be positive, so I no longer need those absolute value signs anymore, okay? All right, so once we're here, then of course, we need to figure out what is the antiderivative of y prime, okay? Well, we know that y prime is just going to be this plus it's the integration constant that we have to write. So we have to take the antiderivative of all 3 of these terms, okay? Well, we know that the antiderivative of this first term is relatively easy, okay? You see here, we just add 1 to the exponent and then divide by what that result is. For this second term here, if we do the integral of natural log of x, we can actually figure out what that is by doing integration by parts. And so I've kind of went through the process here of what it is. The important thing here is to note that this is what the result is. It's x times natural log of x minus x. And of course, you can't see this, but this part is a plus c there, okay? Just saying that, of course, most general antiderivative. So for this portion here, when I take the antiderivative, it's just going to be this. And then, of course, the antiderivative of any constant is that constant times whatever the independent variable is, okay? So from that point, we take everything, we got it in this raw form, we simplify as much as we can. And then, of course, here I could have named this something else, but I chose to keep it this way just to keep the integrity of the problem together. And here we just apply our initial conditions at this point, okay? So here when x is 1, y is 8, we let we let x be 1 and figure out what we have. And so in this case, once we do that and simplify everything, we see that we have 3c plus 3c plus 3d is equal to 20. And then when we look at the first derivative, which is what we had back up here, had the first derivative, and we plug in 1 into that and allow it to equal 6, then we see that we end up getting c is equal to 4. And so since c is equal to 4, we could plug that into here and then essentially figure out what d is. And so you see that we actually do that here. We end up with d is equal to 8/3. So we end up, of course, with c being 4, and of course c 4 plus 2 ends up being 6 here, and of course d is the 8/3. And this is the particular solution to our second order directly integrable ordinary differential equation per the initial conditions that were given. All right, so for our next example, we see we have a first order directly integrable type of equation here. And so this one's pretty easy to do. We could rewrite this as dy is equal to 1 over x squared plus 1 times dx. And of course, for this one, if I wanted to use a definite integral to do it, I could do it this way. So let's say I'll do this, and I'll go from 1 to x here. And let's say 1 to x there. and let's let x equal u, okay? So if that's the case, then I'm going to replace these x's here with u's. And again, I'm doing this just to kind of make everything sort of fit together, okay? And this is the suggestions based upon what we said. If we're going to do definite integrals with these type of situations, what we need to do. So if we do that on the left side, what we end up with is the antiderivative of 1 dy, which is just y, or y of, y of x in this case. And we're going to use net change theorem, evaluate that from 1 to x. On the right side, we see that 1 over u squared plus 1, if we take the antiderivative of that, that's just going to be arctan of u. And we can evaluate that from 1 to x. All right, so now that we have that in place, we can go ahead and finish this up. So we know that if we substitute in x for x, we just get y of x minus y of 1. And on the right side, we'll have arctan of x minus arctan of 1. And of course, here we know that y of 1 is 0. And of course, if we look at arctan, arctan is the same as saying tangent inverse of 1 is equal to some angle. And of course, in this case, this would end up being pi over 4 if we're thinking about it in radians. So we know that all this just ends up being pi over 4. All right, so at the end of the day, this just ends up being, and I'll just drop down here and do it, y of x is equal to arctan of x minus pi over 4. And you notice here, we were able to do that in a nice, clean, concise way, so where we didn't have to figure out what the most general antiderivative of the problem was and then go back and piece together the initial condition stuff to find out what the arbitrary constant was. We kind of just automatically did it in the problem here. All right, so for our next example, we see that we have a first order differential equation. And if we were to divide both sides by x here, what we would see is that we have dy over dx is equal to sine x over x. And of course, we learned before that this is equal to the sinc function. And so we've seen something like this before. If you recall, we had what was called our sine integral function, which we call psi of s, was going to be equal to 1 over x sine of s over s ds. Okay. And so in this instance, remember that x and s are actually equal to one another. So I'm bringing this up because in this problem here, we're basically asking to take the antiderivative of sine x over x, or sinc of x, and we know that that's one of those functions that we really don't want to deal with like that. We would just rather keep it in its definite integral form and possibly use the sine integral function if possible. So we're going to defer to that here. So we're going to rewrite this as dy is equal to, and I'm going to keep it in the sine x over x form here. We'll keep it in this form like that. Okay. All right, so from here, what we want to do is we want to be able to take the definite integral, but we're going to do the suggestion here and do it from 0 to x here. And so if we do that, then of course, from here, we know that the left side will just be y of x, and that'll be evaluated from 0 to x there. On the right side, notice that we actually have what we want. We really don't want to change that, okay? And so since x is able to be equal to s, what we're going to do is change x to s here, here, and here, and leave that the same. So to do that, we're going to say this is sine of s over s ds, okay? And if we do that, then of course, this would be y of x minus y of 0 on the left side. And on the right side, we're just going to leave this as this particular definite integral here, okay? And of course, we know that all of this is just equal to psi of, or sine integral of s here. So what we'll do is just erase all of this and just replace it with sine integral of s to make life simple. All right, so this would be sine of s. And of course, here we know that y of 0 is just -7. And so here, negative times a negative gives us a positive. And then if we subtract 7 from both sides, we'll basically get psi of s minus 7. And so from here, what we would have, of course, since x and s are equal to the same thing, this would just be this at the end of the day. And just want to make sure I got all of my signs right here. Yep. So that is it. Okay, so for our next example, we want to solve an initial value problem containing a piecewise function for a solution. So we have a first order directly integrable differential equation where the first derivative is defined as a piecewise function. And of course, that piecewise function is a stair function. And we're looking at this only for values of x that are less than 4. And we have an initial condition here that y of 0 is equal to 0. So the first thing that we need to do is recall what the stair function is, okay? So if we look here, remember that our stair function looked like this, okay? So it was 0 for all values less than 0, but once we got to x equals 0, it would be 1 in between 0 and 1. Of course, 1 excluding, and then from 1 to 2, it would go up to 2, and 2 to 3, so on and so forth, okay? So what that tells us here is that we need to figure out what this piecewise function is going to look like for all values of x up until 4. So again, we know that it's going to be 0 for all values less than 0. Okay, it's going to be 1 for values of x that include 0, all in between 0 and 1, excluding 1. And then it's going to be 2 for all values in between 1 and 2, excluding 2. And then it's going to be 3 for all values in between 2 and 3, excluding 3. And finally, it's going to be 4 for all values of x in between 3 and 4, excluding 4. And so this is what this piecewise function looks like. And again, if we look at this graph here, we'll see that what we've actually described piecewise is the same thing that we've written out here. Now, notice that if the stair function is this, defined piecewise, then that means that the most general antiderivative of the stair function is just going to be the antiderivatives of each of these constants here. So in this case, all we really need to do is figure out what are going to be the antiderivatives of each of these constants, and we'll have what the antiderivative would be. Okay. So just for a little bit of room, I'm going to move this down here. So let's think about this for a second. So we know that if I was to take the antiderivative of 0, that would just be some constant. Okay. For instance, if I let y equal 2, then of course I know that the derivative of 2, or any constant for that matter, would be 0. So here, what we're going to say is let the antiderivative of 0 be c, and that is going to be valid for values of x that are less than 0. Okay. Now, for all the rest of these, we know that if we have the derivative of something equaling a constant, it had to come from a linear function. Okay. So in the instance of the derivative of something being 1, then that is like saying, hey, the derivative of some function is 1. Where did it come from? Well, we know that the derivative of x, or to be more explicit, 1x, is just 1. So here, if I want to figure out, hey, where the derivative of this came from what? Well, it came from that function. Okay. So here, I'll know that this would be 1x, or just x, plus some other constant, and I'm just going to call it d. And this is going to be valid for values of x in between 0 and 1, excluding 1. And I'm just going to write it here in interval notation just to save some time and space. So if I was to continue that trend here for the rest of these, then of course for 2, the antiderivative of 2 would be 2x plus another constant. And that would be valid for all values in between 1 and 2, excluding 2. And then I would just keep on going and do the rest of them. And so I'll go ahead and just write what the rest of these are, and then we'll continue on with the problem afterwards. And this one, I'll have the constant be named f. And this goes from 2 to 3. And this last one here would be 4g. And this would go from 3 to 4. All right, so we now know that the most general antiderivative of the stair function, which is what y at x would be, is actually going to be this situation here. Okay, so y at x is actually going to be equal to this piecewise function that we're looking at here. Okay, so we have the most general solution, but now what we have to do is figure out what all of these constants are. Okay, and if you recall, we talked about the process that we needed to go through to be able to do problems like these. And one of the things that we mentioned is that we needed to see for each place where the piecewise function switches off from looking like one function to the other, we need to be able to do the limit to the left and to the right of each of those numbers so that we know that that function ends up being continuous. Okay. And so we're going to see what that looks like here. All right, so to start off, if we consider a situation where, of course, we know that y of 0 is equal to 0. And so this initial condition here would be met inside of this particular piece of the piecewise function. Okay. And so we need that in order for us to get started. So if we look here, we'll have y of 0 equals 0. that implies that for this piece of the piecewise function, x plus d, that's going to equal to 0. And of course, we're going to let x equal 0 here. I'm going to fill it in just a second. So we got 0 plus d is equal to 0. And of course, that means that d is equal to 0. Okay. So that lets us know that for at least this portion here, what we're going to end up with is just x here. Okay. So we'll keep that in mind. So now that we have that, the next thing that we need to do is figure out, well, all right, if d is equal to 0 here, we need the switch off from this piece of the piecewise function to this piece to be continuous. And in order for that to happen, we say that the limit as x approaches 0 from the left of this function, which is just going to be c, has to be equal to the limit as x approaches 0 from the right of the same function. And of course, around 0, that's going to be here. And that's going to have to equal to the same value. Okay. Now, we already know that d here is equal to 0. Okay. And if we evaluate this, we know that the limit of any constant is just that constant. And with d equaling 0 here, that means that we can essentially just look at this as what is going to be the limit of x as x approaches 0. Well, guess what? We know from the direct substitution property, all of this could be 0. So that means c is equal to 0. Okay. So what this tells us here is that both c and d are equal to 0. Now we need to do the same exact thing for all the rest of these breaks here. Okay. So what we've done is we've checked in between 0. Now we need to check in between 1, which means we need to deal with these two now. So therefore, we'll do the limit as x approaches 1 from the left of this function here, which is just going to be x, equals limit as x approaches 1 from the right of this particular function here. And that's just going to be 2x plus e. And again, that constant e, we don't know. Now, from here, we know that because of direct substitution property, the limit of x as x approaches 1 from the left, all of this is just going to be 1 because we literally can just plug it in. Here, we know that from the direct substitution property, we can just plug in x here. Of course, 2 times 1 is just 2. So this just lets us know that e, 2 plus e, if we subtract 2 from both sides, e will just be -1. Okay. So we need to do it 2 more times. So we've taken care of the first 2. So now the next 2 that we need to look at are these 2 here. And so we repeat the process again. So limit as x approaches 2 from the left, and this will be what it will be from the left, 2x plus e, and remember e is -1, and then limit as x approaches 2 from the right of 3x plus f. And of course here on the left side, we can just plug in 2 there. 2 times 2 minus 1. On the right side, plug in the 2 plus f. And of course, on the left side here, all of this will just end up being 3. This is 6. So this means that f will end up being -3. And then finally, we need to do this one last time for both of these pieces of the piecewise function. So we got limit as x approaches 3 from the left of 3x plus f, and f is -3. Limit as x approaches 3 from the right of 4x plus g. And of course here, if we plug in 3 times 3 minus 3 equals, direct substitution property allows us to be able to plug in 3 here. And again, all we have to do is just figure out what g is at that point. And so 3 times 3 is 9. 9 minus 3 is 6. And 4 times 3 is 12. So this lets us know that g here is going to be -6. And so now that we have all that together, I'll come back up here and we'll actually say what our answer is. So here we know that this is going to be 0 for values of x less than 0. It's going to be x for values of x in between 0 and 1. It's going to be 2x minus 1 for values of x in between 1 and 2. I'm going to do 3x minus 3 for values of x in between 2 and 3. And the last one, g, was -6. Okay. So this would be 4x minus 6. And that would be in between 3 and 4. And so that would be our final answer to this particular question. So if you want to know what is the answer, well, this is the actual answer to our question. So for our last example, now that you've seen an example of how we actually use piecewise functions in solving directly integral type of equations and how limits and all this stuff comes into play, we're going to do one more example here where we have dy over dx is equal to a step function where our initial condition is when x is 0, y is 0. So for this one, again, since we've already seen that, I'm just going to switch over and kind of talk through a problem I've already worked out. So we'll just look at that, make sure that we understand everything, and wrap things up here. So if you see here, we know that this is a directly integrable type of equation of the first order. And so we know that we can rewrite this as just dy as equal to step function times dx here. And so if we take the indefinite integral of both sides, we recall that our step function here is represented this way in terms of piecewise functions. Okay. So remember, the step function is it's 0 up until x is greater than or equal to 0, then it steps up 1 unit. And so that's essentially what it is. Of course, here you have closed circle, there you have open circle. And so that's what this piecewise function is trying to communicate. So from this point, we understand if I'm taking the antiderivative of this piecewise function, then it means I have to take the antiderivative of each piece of the piecewise function. And we're assuming that each piece of the piecewise function is continuous on its interval. Okay? And so from here, we know that the antiderivative of any constant, antiderivative of 0 is some constant, and we know that the antiderivative of 1 is just going to be 1 times the independent variable, which is just x. And then, of course, that will be plus some arbitrary integration constant. So we see here that in general, note here that this is going to be a situation where the antiderivative of dy is just going to be y of x. So all this is just going to be y of x is equal to this. And we have the integration constants built into this part, so we don't have to worry about writing it here. And so we know that these are constants. And again, since y of x is equal to indefinite integral of 1 dy is a solution, it follows that y of x must be continuous for all real numbers x. And so that's what you see here. And if it's going to be continuous for all real numbers, then it should also be continuous at x equals 0. And so not sure why I have 1 here, but that should be 0. So because of that, of course, the main deal here is that the function changes what it looks like from a constant function to a linear function at x equals 0. So that's why we're particularly worried about is the function continuous, or the behavior of the function at x equals 0. So similar to example 3a that we did earlier, if we know that the behavior, that is to say the limit of y of x as x approaches 0 from both the left and the right, we know that it's going to have the same value of y of 0 at x equals 0. Okay, so we essentially just take the limit as x approaches 0 on the left for this function equals limit as x approaches 0 on the right of this function. And that's what you see here. And we know, again, that in order for all this to work and to have everything connected, it is going to have to be equal to y of 0 here. And of course, if we go back up to the top here, we know y of 0 is equal to 0. So what that essentially means here is that this is equal to 0. And so the limit of any constant is just that constant. The limit of x times, x plus d, where we know in this case, we're going to plug in 0 for x. So we got 0 there plus d. And we see here that c is going to be equal to d, which is going to be equal to 0. Okay. And so because of that, we now know that both c and d are 0. So if I plug this in, this will be 0 here, and x plus 0 is just x. So we see that our solution to this first order directly integrable equation will just be this particular piecewise function, which is indeed just the step function, the antiderivative of the step function itself. Okay. And if you recognize this, this is actually the ramp function. Okay. So remember, the ramp function is a function that all values of x are 0 up until you get to 0, and then it goes up like this, and it looks like the function y is equal to x. And so that is essentially what that particular piecewise function is. All right, so with that being said, this concludes the video on directly integrable ordinary differential equations, as well as how to deal with solving these types of ordinary differential equations, both using definite and indefinite integrals. We also went over how to solve ordinary differential equations where they're directly integrable and the right side of the equation is defined as a piecewise function. Hope this video helped. Take care.